Okay, so if not, we were basically, we had introduced the raising and the lowering operators. Raising operator, it had the action that when it's acting on a state with J3 eigenvalue m, it increased that eigenvalue by 1. And we are assuming that all these states, all these states are normalized and different values of the J3 eigenvalues are orthogonal. But this implies that there should be a proportionality constant, and we shall see that, in fact, the proportionality constant has a very important role to play. Similarly, for J minus, when it acted on an eigenstate of J3, it decreased the eigenvalue of J3 by 1. And we introduced a different set of proportionality constant that we label D. And in principle, it was different from C. But we found, by doing a bit of clever manipulation, by taking inner product of these equations, that we found that they are actually not different, that they are related by complex conjugation in this fashion. Okay, so we only have to deal with one set of these operators. So that's where we ended. So that means that we can write J minus acting on lambda m to be C star m minus 1. Well, sometimes I'll forget to write the lambda eigenvalue, because as long as we are in a given irreducible representation, the lambda eigenvalue is the same for all states, right? Is that clear? That if lambda, for an irreducible representation, lambda is the same for all states.
Because of Schur's lemma.
Exactly. Because of Schur's lemma and J squared, the lambda eigenvalue is just a J squared eigenvalue. So similarly, we can take this equation and take its complex conjugation. We can complex conjugate this equation and get the conjugate. So this becomes J plus, and then we have Cm, and then m minus lambda m minus 1. But here we have the Hermitian conjugate state, the bra. Okay. Now, one of the things we assume that we are constructing, so this is by assumption, that we are constructing the finite dimensional representations of SU2. Okay. So what does this mean? This means that, the J3 eigenvalue, must have a maximum, okay? And let's call that maximum, say, J prime, and a minimum, okay? Because if not, then we would have an infinite number of basis states, right? And then we would have an infinite dimensional representation. Is that clear? So this is by assumption, right? because we're looking for the finite dimensional unitary representation. There is an infinite dimensional unitary representation of this algebra, but that's a separate issue. We are not going to talk about that right now. That's something one does discuss in quantum mechanics.
So each eigenvalue corresponds to a state. Is that right?
Yeah, each eigenvalue of J3 corresponds to a linearly independent basis state.
Okay, see.
And they're all orthogonal. Remember that in the last lecture, we talked about how given a set of mutually commuting Hermitian operators, we can find simultaneous eigenvectors, and those simultaneous eigenvectors can be normalized and can be chosen to be orthogonal so that they provide us with a complete basis for the vector space we are working with. Okay. So these vector spaces are the vector spaces that these operators are acting on are finite dimensional, and any vector in that vector space psi will be given by some, linear combination of these vectors, right? So we are dealing with these vectors, the basis vectors. More generally, I can write them that I, J, the inner product of I and J gives you this, okay? And this is essentially this equation, but I'm fixing lambda prime to be lambda because I'm in a given irreducible representation so that I can set this guy to be 1. Okay, Saif, is that clear?
Yeah, that makes sense.
Okay, good. All right, so now we use the fact that there is a maximum value of M. Okay, let me call the maximum value of M, not J prime, but J. Okay, let's call it J. And the minimum value of M, J prime, right? So what does this mean? This means that if I were to apply J plus on that highest weight state, so this is known as the highest weight state, what would I get?
You should get it back, I guess, because you can't go higher.
If we got it back, then that would not be consistent with the commutation relationship that J plus has with J3. Remember that J3, J plus is equal to J plus. So if I got it back, if I got the same state, yes, in some sense you're right, I should get it back, but what should be the constant of proportionality? I actually would get, yeah, so.
You would get 0?
Yes, exactly. You get 0, right? That's the only way to be consistent with the fact that we have a finite dimensional vector space and this equation. Okay?
Yeah, makes sense.
Okay. And then if I apply J minus on the lowest weight state, which is where M is J prime, then I would get 0 as well. Okay? So this sort of representation theory is known as the highest weight, this is called the highest weight, okay? And mathematicians work with the lowest weights sometimes. So mathematicians like to work with the lowest, like mathematicians and physicists can never agree on the sign, so yeah. All right, good. So now, we really haven't used the third equation of early algebra, which was the commutator of J plus and J minus. It is time for us to bring this out now, okay? So how do we bring this? How do we use this? So, we know that if we were to use, say, if we were to take the highest weight state and apply J minus on it, and so if I want to have this thing non-zero, right? So what should I put here? If I want to have this non-zero, I put here.
Sir, same cat as you wrote.
Exactly. Because this thing acting on this guy will lower the eigenvalue, because this will be the conjugate of J minus acting on something. So yeah, so it'll be this. So if I do this, then I use this commutation relationship, then on the right hand side, I'm going to get bra of lambda j, j minus j plus lambda j, and then plus 2 lambda j, j3 lambda j, okay? So, but j plus acting on the highest weight state gives me, according to this equation, it should give me 0, right? Because this is the maximal weight state. So this should give me 0, right? Similarly, this will also give me 0, but 1 is enough. So we get 0 plus, now J3 acting on this will give me the eigenvalue, which is J. So here I will get 2J and lambda J, lambda J. J3 does not change its eigenvalue. These are all eigenvectors of J3. So on the left-hand side, on the other hand, I have, if I apply J minus on something, I get, what do I get? Here. J minus acting on something gives me I get the C value of that with that index. So on the left-hand side, so let me make some space here. Let me move this slightly to the right. So on the left-hand side, from this thing, I will get CJ star. And from this thing, I will get CJ. And so this guy is 1, right? Because these are all normalized stuff. So here, we will get similarly, because I don't have space, I'm writing it like this. We will have lambda j minus 1, bra of that, and lambda j minus 1, which is also 1. So this equation then gives me that the modulus of Cj squared is 2j. Okay, is that clear?
Yes.
So we have found one of the constants. That is very exciting.